I'm recording now. All right, everybody. So the definition of analysis of variance is on the screen today. And it's really good that we start here and talk about this discussion, because this is going to take us to understanding a little bit about the analysis, the ANOVA. And I hope in a way that will make it so that this can stick with what we're doing. I hate when the camera is over there. I keep looking at myself and it looks awful. There we go, right in the middle. All right. The definition that we have is a one-way analysis of variance, short nickname ANOVA. Now, for many of you, I would imagine the ANOVA is sometimes quite a mystery. I'm hoping that today's conversation will take that mystery away. However, y'all need to be with me, right? Again, me going over it and me trying to demystify it doesn't really work if we're on the other side of the cutoff camera, not really paying attention. It's a method of testing the equality of 3 or more population means by analyzing sample variances. And you know what? I think this comment right here really illustrates a dilemma that you think about. When we're doing an ANOVA, we're really interested in the means, right? Usually the means of a sample. Now, in order for us to make inferences about the mean from the sample, we're going to be using these statistics that will assume knowledge of the population, right? But it's a method used to test the equality of 3 or more. And this is what's one of the benefits of this. It's not just if you want to do 2 means. We did 2 means in chapter 9 when we were doing paired samples. We did dependent samples, a t-test. We did independent samples, t-test. That's when we had 2, right? We're not going to do that if we have 3 or more samples, or we have 3 or more means. What we're going to use is analysis of variance. And there's going to be so much value in doing that. And we'll discuss that today. But looking at this definition, it's a method of testing the equality, right? Now, this is the key word, the equality of 3 or more means. And they do that equality, in my mind, indirectly. The primary focus isn't necessarily on the means itself. It's whether the means are equal, whether the means are similar, whether they have similar traits. And the trait that we're looking at that's similar is the variance. So we're going to be looking at 3 means and finding out whether their variances are similar. That's why it's a one-way analysis of variance. But yet when you're the researcher and you're doing it, our primary focus is always on the means. Like I always used to wonder when I was an undergrad, like where in the world does the VA come from the variance? Because what I care about is the mean. And the mean is probably the most essential thing that we put into the ANOVA typically. However, we do it, just like it says right here, by analyzing sample variances. And that's kind of the inference that I was saying before. We're going to analyze the sample variance to learn something about the population means, right? As always, that's what inferential stats are all about. We go from a sample to make inferences to a population. So sample will allow us to make, I'm going to make it with the letter I, inferences about a population. All right, so let me clear that just to get this off the screen, right? Now, one-way analysis of variance is used with data characterized by one factor. Now, we're going to come back a little bit later to this little factor note, but that is always key to sit back and understand what a factor is. One of the things that you guys might be familiar with is it says one factor. It's also called one treatment. But really what really helps many people is to understand the variables that we've been using for years in psychology. And what we've been referring to that really relates to this is one independent variable. All of those are the same. One factor, one treatment, or one independent, spelled that wrong, oh my goodness. 2 extra words in there, all the same. One-way analysis of variance is used when data is characterized by one independent variable. Say it again. One-way analysis of variance is used when data characterized by one factor. Same thing. Say it again. One-way analysis of variance is used with data categorized with one treatment, all the same thing. Meaning there's one characteristic. Doesn't matter what we call this characteristic, but that means there's one characteristic used to separate the sample data into different categories. All right, anybody lost so far? Okay, I'm gonna keep it moving. Actually, first I'm gonna clear this off the screen first. Okay, now we want to start off by doing the sample problem. I need a volunteer to read the sample problem. This sample problem is something that we're going to use to talk about the analysis of variance. But it starts off with this chapter talking about, does exposure to lead, that's a big thing, lead exposure, affect IQ scores of children? So I'm actually going to need 2 people willing to, actually I'll do 3 people willing to read. And I'll stop you guys at the appropriate places, I think, that'll make it equal. And what I want to do is this, instead of calling people out, raise your hand in the chat, like the little chat thing, and that'll let me know that you're willing to read this portion of it. All right, so we got Jasmine, that's 1. We need another individual to read. All right, we got another hand up. That is Nareese. Actually, Nareese, you clapping, but that's same thing. All right, 1 more. Nareese and Jasmine. All right, we're going to start with Nareese. All right, do you mind reading for us?
No.
All right, go ahead.
An important environment/health study involved children who lived within 7 kilometers of a large ore smelter in El Paso, Texas. A smelter is used to melt that ore in order to separate the metals in it. Because the smelter emitted lead pollution, there was a concern that these children will somehow suffer. The focus of this chapter problem is to investigate the possible effect of lead exposure on performance IQ scores as measured by the
Wechsler intelligence test. All right. Now, who can read? All right, Jasmine, you're next. Start reading off in the parentheses. Usually I tell people to skip the parentheses, but I want to make sure we're comfortable with this. So start reading right here in the parentheses for us, if you can, please.
A full IQ score is a combination of a performance IQ score and a verbal IQ score. The performance test includes components such as picture analysis, picture arrangement, and matching patterns. Data from the study are included in data set 7, IQ and lead, and Appendix B.
Okay, we can stop there. We can stop there. Thank you. All right. Now, you know what? I feel bad because I asked for some volunteers and we don't got people in here, right? I need another 3rd volunteer who can wrap this up for us.
I'll read.
Okay. All right. The other Jasmine, thank you so much. All right.
Based on measured lead levels, the children were partitioned into a low lead level group, a medium lead level group, or a high level level group.
Okay. Now you finished it off. That's perfect. Now, I'm not going to do that just yet, right? But there's a whole lot from this that we talked about. I'm just going to go back over what we talked about to make sure that we're really getting it, right? So we got these poor children. I ain't going to say they poor, right? They live in Texas. They're about 4 miles away from an ore smelter, right? Now you might be thinking like, what the hell is an ore smelter? I don't know either. But they talk about how ore is used to separate metals, right? And it's emitting lead pollution. So these kids, it's not even like lead paint in the house. It's just in the air. I live in Delaware and we used to have a factory. I'm pointing the wrong way. A factory down the street that used to mess up the pollution. Honestly, when it shut down, actually it's funny, it wasn't even in Delaware. Actually, no, it is in Delaware. It's on the bay right into Philadelphia. But I used to sit back there and be upset. When it closed down and it's probably now at maybe 20% of full capacity, some people were unhappy. That's because they used to work and their families used to work at the factory. But I was happy as hell. And my children actually saw a difference in their allergies as a result of the air pollution decreasing significantly. We're putting in 1/5 as much pollution at this factory than we used to, right? Then we go into detail about the IQ score, right? It's not just, oh, how smart are you? we're looking at a couple of things. We got verbal IQ score. We got a performance IQ score, which is talking about picture analysis, arrangement, and then kind of like matching patterns, right? So it's not just doing a math test. This is really what IQ is. It's about literally the ability to critically think and to manipulate things in your environment. And that makes sense. That's why they have picture analysis, picture arrangement, and matching patterns. Now, as we get older, reading is matching patterns. Statistics is matching patterns. Filling in equations that we're doing is using arrangements and analyzing the equations. Your IQ preps you and will set you on for success many ways later. Now, they go into detail what Jasmine told us, the other Jasmine, they measured blood lead levels. Oof, you're getting real right here. And as a result of what they recorded, the children were partitioned into a low lead level group, a medium lead level group, or a high lead level group, right? This is a real problem that people really deal with when you live in neighborhoods and where you're at. All right, so let me clean this out, annotate, clear. This right here is the data. Just like it said, it partitioned the data into a low blood level group. Ooh, good thing is there's a lot of kids who are in this low level group. I don't want to count it, but it's a lot more kids in the low blood lead level group. We got some kids in the medium blood lead level group. And then we also got kids who are in the high blood lead level group. I don't know what they were doing or where they live. Maybe they live closer. But this is what the data looks like. Now, each one of these values right here represents what? I want to make sure you're following me.
The level of lead found in each person's blood.
Yep. Each and every one of these is the blood lead level. And of course, we categorize them from the groups like we mentioned before. Excellent. Thank you. Clear this. All right. Now I'm going to read this, right? The performance IQs are included in table 12.1. Before jumping into the application of a particular statistical method, we should first explore the data. Sample statistics are included in the table below, right? So let's sit back and look at this. Look at the sample size. Remember, there's a little bit more. This right here, you can clearly say it. And this is the beauty of using sample statistics because it helps you summarize information in ways that make sense, right? I was looking at that chart. I didn't feel like counting. There are 78 children who are in the low blood lead level group. How many children are in the medium blood level group?
22.
All right. And there's one less than that in the high blood lead level group. All right. Now we learn so much information from looking at these descriptive stats. That's not what this class is about, not now, but look at this. What is the mean low blood lead level group?
Uh, 102.7.
102.7. That's so funny. When I grew up, our favorite radio station was V103 and it was 102.7. That number just sticks out to me. All right. Now, here's the thing that's kind of confusing to me. I don't get it, but look at this. The medium blood level group, blood lead level, and the high blood lead level, they're almost the same. I mean, when you look at the mean, and that goes to show you that, again, you can't always look at the mean. We got to go into detail and we got to look at some other analyses. We can't eyeball analyses. That's why we have this stats class, right? Now, ooh, here goes something. I think I'm going to get somebody, at least I'm hoping to, right? What in the world is S? What does S stand for? This is basic, man. It's going back to chapter 3, real talk.
Standard deviation.
Standard deviation. You go, girl. Come in. No, I'm on class. Standard deviation for the low blood level group is 16.8. Standard deviation for the medium blood level is 15.5. Standard deviation for the high blood level is 11.4. Now, when we look into the data more closely and we look at them more, you see there are differences. Even though I said the means aren't that different, the standard deviation is different. Now, the distribution, again, talking about they're all approximately normal. That's good. Outliers, again, due to the fact that there's 78, there's probably more likely to have outliers than in the medium group and the high, but just because there's more numbers, mistakes are going to happen. Okay, so let's clear this. Let's go on to what else was being stated in this. See the following box plots of 3 sets of performance IQ scores. Informal and subjective comparisons. Now, what does this mean? Informal is just us kind of eyeballing it. Now, we're in a stats class, so we know that we're not going to do that. But this right here is just kind of eyeballing it. Ooh, it looked different. So what? It looks different. That's the informal and subjective comparisons. Somebody might be like, ooh, look at these little dots right here. It looks neat. That's informal and that's subjective comparisons. I don't care anything about that. We're in stats. We're trying to find out whether it is statistically significant or significantly different from one another. Right? Now, looking at these subjective comparisons, you can see a couple of things. And let's follow what this article is saying. Who can read what I just highlighted right here? This is one of those things that we just got from looking at it.
The low
group.
Sorry.
We got more to read. So now Reese, should go first, and whoever was else talking will go next.
The low group has a mean that is somewhat higher than the means of the medium in high groups.
Okay. All right. And then in addition to that, we also see what? What else did it say from this informal and subjective approach? Who else was trying to read?
Me. The box plot all overlap, so difference do not appear to be dramatic.
Okay.
Dramatic, yeah.
Yeah, dramatic. Now, let me tell you what they mean by overlapping, right? Now, in the event that we look at these things, when you're looking at a box plot, you guys might remember this from before. I might have said it from before, right? Imagine that this box plot stopped here. Due to the fact that the mean and the standard deviation, the quartiles are here, since these ranges overlap with each other, like look at this, these variables overlap with that first. Now, if this information right here didn't overlap, like if this right here, because this is on a number line right here at the bottom, right? If this value was over here and the box was here and it stopped there and it stopped here and it didn't overlap with this, that would be more likely thinking it's significant, right? I hope y'all can see what I'm trying to write right here. It does look a hot mess, right? So we got this right there. That's a little box plot. Filling in, I probably should have the black line to do this. But if the box plot looked like this and there was absolutely no overlap between the two, that would actually be a lot better. Then you can sit back and be like, ooh, that's significant. But due to the fact that there's so much overlap between these things, yeah, looking at this, the researcher and the observer just being like, yeah, it doesn't look anything significant. All these look the same. There's probably no difference between them. That's what we're saying. The differences do not appear to be dramatic, but we need more formal methods to recognize if there's any significant difference. Because again, what we look at, these assumptions, they're good techniques, but they don't always tell you the truth. So we're going to use now this is going into what I already said before. So I'm actually going to skip this. I'm not going to go over this. I already talked about these points that I was about to read. Okay. Going into this, there's 3 things that we want to get into. All right. Now, I'm not hearing from a lot of people in the classroom, so I am going to ask for some readers. And I want someone to read what's next to number 1, 2, and 3. And I'm hoping to get people that have not spoken yet, or at least a combination of before and after speakers. All right. Who can read up here for us?
I can read
All right, go ahead, Jasmine.
the key concepts, right?
Yep.
In this section, we introduced the method of one-way analysis of variance, which is used for test of hypothesis that 3 or more populations have means that are all equal, as in, I don't know how to read that notation.
All right, but this is, I'll sit back and help you, right? This means, ooh, somebody can let me, who else can let me know? What kind of hypothesis?
That's the null hypothesis.
Ah, okay, so she knew that. See, I was trying to spread the love a little bit, right? But that's the null hypothesis, right? And it's saying that the population mean of the first group equals the population mean of the second group equals the population mean of the third group. So all these population means are equal.
Okay.
All right, go ahead. You finish reading for us?
Because the calculations are very complicated, we emphasize the interpretation of results obtained by using technology.
Okay, now we're going to emphasize them, but we are going to play a little bit today with making you guys see it. There's a table that I'll tell you, I think I taught this course twice before I understood it. And that was probably like in my second time looking at it. And I think that what we can do today will help us do it. The definition we already read, so I'm not going to go into that too much. But I need another individual to read the third case.
Again,
All right, go ahead, Naris.
the term treatment is used because early applications of analysis of variance involved agricultural experiments in which different plots of farmland were treated with different fertilizers, seed types, insecticides, and so on. Table 12-1 uses the one treatment or factor of blood lead level. The factor has 3 different categories: low, medium, and high blood levels, as defined in data set 7 in Appendix B.
Okay, it's a lot of information right here, right? So let's sit back there and do this. They talking about agricultural experiment. Dr. Hughes would be happy. All right, so annotate. Let me clear all this. Then we're going to go into these 3 questions a little bit deeper, right? Now, based on the chapter problem, I want y'all to tell me what you think the hypothesis would be. And we're going to mimic and duplicate what we already done and what we kind of learned from going through this when Jasmine was reading. How would we write this, right? For the chapter problem. I'll help y'all out with the hardest part.
There is no difference
Okay,
among
now you know what? Now I'm gonna pause you because you know what? You're telling me the claim, right? And I'm gonna include that, right? There is no difference. Keep going.
among population means in lead levels.
All right. Now she did it in English, right? Now we got some skills we've been learning in this whole class. I want y'all to give it to me in alien. And Jasmine, you're not necessarily off the hook. You could jump back in if you could put it in alien for us. All right. So how would we write this in alien?
When they will all be equal to each other, right?
All right. So they all equal. So I'm gonna have one of these equals one of these equals. Now, how many do I need?
3.
3 of them. Okay. Now, these are numbered 1, 2, and 3, right? So we need 3. What could we do as a subscript so that we can distinguish them?
Like low, medium, and high. So L, M, and
You go. Low, medium, and then high. That's it. That's it. So that's just application from what we've seen and what we've done, and being able to write these hypotheses is going to be a part of the homework. So that's why I want to make sure we go over this so that we have it. Good job, guys. All right. Now here's a question. What the one factor that we talk about in the chapter problem. Now, it could be the one factor, it could be the one treatment, it could be the one independent variable.
Lead levels.
All right, lead levels. I'm going to say blood lead levels. Okay. Now, here's the issue though. I don't understand because y'all just said before that there were 3 samples, right? So even though we got the one factor, we got the low blood level, blood lead level. We got the medium blood lead level. And we got the high blood lead level. Right? So one factor, but that one factor has 3 levels. And this is how the ANOVA is different from the t-test. When we did the t-test would only be able to compare 2 of these. The t-test could look at low blood level and the medium blood level and tell you if it's significant. Or the t-test could look at the low blood level and compare it to the high blood level and tell you if it's different. Or a t-test could compare the medium blood level to the high blood level. There's 3 possibilities, 1, 2, 3, right? But the t-test can only do 2 at a time. Our ANOVA is pretty damn powerful because it can do all these 3 possibilities in one test. And that is why we definitely use this. And the benefit is this: if we were to do a t-test on this right here, we'd have an alpha, probably if we're stats, psychologists, at 0.5, right? When we do this test over here, right, we'd have an alpha of equal what? 0.05. And then we'd have another alpha of 0.05. Now, we done ran the gamut, we done rolled the dice 3 times. We essentially need to add these things up to find out our risk of making a mistake. So our total risk of making a mistake is no longer 0.05, which is what we want. Our alpha is really 1.5 because we did 3 different tests all at once. And that is why the ANOVA is that much more powerful, because we can do all this and still have just our ANOVA set at 0.05.
So I have a question.
Okay.
So so is our alpha, does our alpha actually become 1.15, or is it more so like it's the alpha is still 0.05, but we're looking for a number? I don't know, does it even make sense, or is that the same thing?
No, but let me tell you one thing I want to make sure I clarify on what you just said is this. Remember, if we were to do a t-test, right? This is imagining we're doing a t-test. That t-test would have an alpha of 0.05. And then if we did a t-test of low and medium, it would have an alpha of 0.05. And if we did a t-test of medium and high, they each would have an alpha of 0.05. So if we did 3 different t-tests, each with an alpha of 0.05, even though each test has 0.05, right? At the end of the day, the risk of the mistakes that we could have done in this experiment, the total risk is 0.15. And that's why researchers oftentimes will get research that can't be replicated or is not true. Because since they didn't know what we know, you might as well do an ANOVA if you got 3 levels. But we hit at elsewhere university that isn't paying attention in stats, right? They're with us, they just ain't paying attention. They gonna run 3 t-tests and they gonna get a result that says, oh, one of these is significant. They're gonna put their name, reputation on the line, and it was a mistake because they inflated their chance of making a mistake by doing 3 tests, each at 0.5. So at the end, their overall risk of making a mistake was 0.15. Even though they never sat down and said, yeah, I want to do a t-test and be 0.15. They just did it. They didn't know, they didn't listen, and they made a mistake. That help, Jasmine?
Yeah, I think so. So our confidence level actually becomes 0.15.
No. A confidence level, as I was saying, the test, you're never going to sit down and do a test and say my alpha is 0.15. I'm just saying, since they don't know, since they did 3 tests at 0.05, right? They actually have an overall confidence level of 0.15, which is not what anybody would ever want. And that's because they don't know.
So they have room in that. So anything, huh?
Go ahead. I didn't hear what you said last.
So like anything, like less than 0.15 would still be okay.
No, the only thing that we say is okay in psychology is 0.05.
Okay.
Anything. So even if you do 2 of them, you add them up, it's above 0.05. So it's a problem. This right here, this is not good. This alpha of 0.015, that is not good. And that is why we're going to do the ANOVA, because the ANOVA will allow us to compare these 3 groups. And when we do it in 3 groups in one test, our alpha is 0.05. This is never acceptable. Don't try to sit back and look at this and be like, oh, but I can do it this way. No. This approach of 3 different t-tests is never acceptable. And that's why we learn the one-way ANOVA or the ANOVA. All right, let me clear this off the screen. Move on to the next problem. What would be the 3 population means? Yeah, we kind of already did that already. Okay, now I'm going to read this just to make sure we get through it, right? We're going to talk about the F distribution. Now, always in this class, one of the things I always tell you to do is you want to find out if you reject the null hypothesis. We always want to sketch, right? And then we're going to label where this thing is, and then we also shade it in, right? Now, many times I'm using like a normal distribution, right? I want to bring your attention to the fact that right now we're doing the F distribution. And just like the chi-square distribution, the F distribution is not normal. So if I were to sketch, label, and shade something like this, right, that's not right. The F distribution is not normal. It's a little bit skewed. And I'll show you some examples, right? So there is a different F distribution for each different pair. We'll talk about getting complicated. Read this. This is some dropping some facts right here. There is a different F distribution for each different pair of degrees of freedom. So we don't just have 1 degrees of freedom when we're doing this. We have a pair, and we'll go into it. You can see it right here. There's a degrees of freedom for the between sample, and there's a degrees of freedom for the within sample, right? So that's what the pair is. Some facts about this. The F distribution is not symmetric, which is what I talked about. A normal distribution is not appropriate. It's skewed right. Another thing is the F distribution cannot be negative. So if you get an F value that's negative, you did something wrong. Something else is that the exact shape of the F distribution depends on the 2 different degrees of freedom. That means depending on the degrees of freedom, this isn't really new, but depending on the degrees of freedom, your distribution will look different, right? And let me show you how it looks different and how easily it looks different. This right here, shrinking this information, which we already read. Hopefully y'all were with me paying attention, right? Now we got 2 degrees of freedom. The numerator degrees of freedom talks about the number of groups we've had, right? So degrees of freedom for the numerator is k minus 1. In this example, we had 4 groups, which is K, minus 1 would give us a value of 3. So these numbers are not with the chapter problem anymore, right? Now, how many variables do we have in the groups, or how many values do we have in the group? We have the denominator, degrees of freedom, right here. But look at what happens as our sample size kind of increases, right? Looking at this, it's not symmetric, as you can see. That's rule number 1. I just said this. The F distribution is not symmetric. It's skewed to the right. This is not symmetric, and it's skewed to the right. I'm not lying to you. The values of F cannot be negative. It starts at 1 and they increase. There's no negative side of this distribution, right? And the last thing I can't show you on this one slide, but saying the exact shape depends on the 2 different degrees of freedom. This is of a numerator of 3 and a denominator of 3. This is what the F distribution looks like. And we would use this to determine whether or not we fail to reject or reject the null hypothesis. Let's look and see what happens as we increase sample size, and we're going to change the denominator. This next slide. Now we increase the sample size. This distribution has changed. Now it's still not symmetric. It's still skewed to the right. It still cannot be negative, but as you can see, it changed. And it changed quite a bit. Let's see what happens when we add more. Now we increase the sample size, so there's more participants in each of the groups that we have. Again, it has changed drastically from this, more so from this, and then even more now. But I'm not done yet. Let's sit back and increase to 29. Now you know what? Look, it's not changing that much. It is changing, but not that much. Let's go up even higher to 59. It's still not changing that much. But it is unique. So it changes the exact shape of the F distribution, does depend on degrees of freedom. But as you increase your sample size, right, it doesn't get much more. And actually the magic number is usually around 30 is where you can be confident. So when you're doing experiments and you have about 30 people in each of the conditions, yeah, your distribution isn't really going to change much. And so you'll be able to find what you want to find in your experiment. So that's showing you how the F distribution behaves. All right. Now, what does this relate to? In the back of the book, we'll go to the distribution. I forget what page this is on, right? But in the back of the book, they'll have the distribution is table A5. We would look at, we first started off with 3 numerator degrees of freedom and then 3 in the group. Let's see if I can make this a little bit bigger. Okay, here we go. The first set that we looked at was this. We had a 3 numerator, 3 denominator. In order to reject the null hypothesis, our F value would have to be greater than, I hope y'all can see that, 15.439. That's a high F value. Now it gets easier if we increase our sample. So we still have a degrees of freedom of 3, but then there's about 9 people in each of the conditions, right? Now our F value is 5. Now that's still a little high, I ain't gonna lie, right? But it's easier. You see how it's getting easier. Around the 3s, in my mind, is where psychology oftentimes get F's values and where it's easy to reject a null hypothesis. So when we went from 3 numerator degrees of freedom down to 19 in the denominator, we got one of those reasonable F values. The last one we went up for was 3 and 29. The F critical that we need to obtain in order to reject the null hypothesis is now reasonable, 3.6. And also realize that, again, we can go real high. This graph, you can't see it, but once you get beyond 30, the decrease isn't significant that much, but it does still kind of decrease. Once we get to 59, which is I think where we stop, but this doesn't have 59, it has 60, so it's real close to it. The F critical that we would have to reject is a value of 3.3425. So the reason why we have this table in the back of the book is because of what we're showing you right here. these distributions are unique depending on the aspects and characteristics of your sample. So we need these data charts in the back of the book to make sense of it. And then we use the degrees of freedom, and we'll go find what do we need? What do we need to reject that null hypothesis? All right, I am a little upset, but we're not, and upset's the wrong word, but we're not going to finish, I think, where I wanted to go today. Right now, this is what we're going to do. I am going to talk about this just a little bit. When it comes down to the F distribution, which is that table I showed in the back of the book, right? F can be calculated a number of ways, but it essentially compares the variance between samples and it compares the variance within samples. That's what an ANOVA does. And that's why an ANOVA is able to use more than 3 groups, because at the end of the day, it's not really caring about comparing the means in one group to another. It's looking at the variance, and the variance can be used to calculate and reflect all 3 levels, 4 levels, 5 levels. I don't care how many levels you got. I'm going to look at the variance between those samples, right? And then I'm also going to look at the variance within those samples. So it doesn't matter if you have 2 samples. No, you don't do 2. Doesn't matter if you have 3 samples, 4 samples, 5, up to 6, even more. Since I'm looking at the variance within, the ANOVA can, honestly, I say theoretically, it can cover and account for any unknown number of levels. But again, when you have that many levels, you get kind of confused with your experiment. Now, reading this is just reiterating what I've already said. The numerator of the F test statistic measures variation between samples. Just said that. The estimate of variance in the denominator, down bottom, depends only on the sample variances and is not affected by differences among the sample means, right? So this is saying it's only impacted by the sample variance. So we're looking in the samples to see how much variance, AKA variability, exists, right? It doesn't really care about how different the sample means are. It's just looking at inside each of the samples, how much chaos, variability, variance is going on. As a result of that, they argue that sample means that are close in value result in a small F test statistic. And that's because the between sample variance, right, is small. There's no difference. So the numerator is small, right? Since the numerator is small, you're going to have kind of a small F value. But you'll have a large P value, because I'm just going to leave P value out. I don't even want to talk about that. But if your sample means are far apart, right, there's a great difference. That means your numerator is going to be high. That means your numerator could be like 9, and let's say your denominator is 2, right? 9 divided by 2, that's a big number. That's 4.5, right? So if your numerator is large, then that means you're going to have a, no, if your numerator is large or your difference between those samples is large, you'll have a large F value. If the difference between your samples is small, that means you'll have a small F value. And that's because the value that's on the numerator up top, you all know how numbers work a little bit, right? The number on top will be small. That's like comparing 9 divided by 2. And we're saying that 9 reflects the variance between samples, right? You compare that to a 1 divided by 2. This value is 4.5. That's a good F value. This value has an F value of 0.5. That's a difference. And that's because the numerator is talking about the difference between the means. So if you have a big difference between the means, we got a big F value. If we have a small difference between the means, we have a small F value. And one of these is more likely to reject the null hypothesis, but we'll get into that next class. 1 minute past the end of class, guys. I don't want to hold y'all longer. If you have any questions, you can stick around, but I am done with what I got to say.